Alright guys, in this video we'll continue on 5.1 and let's take a look at what's going to happen if the random variables are independent. So first of all, let's take a look at what we went over before in chapter 2. Let me pull out the marker. In chapter 2, we pointed out that one way of defining independence of two events is via the conditional, even the condition probability of A intersection B is equal to the probability of A times probability of B. And here's an analogous definition for the independence of two random variables. So two random variables x and y are said to be independent if for every pair of x and y values, so if they are discrete, the joint PMF x and y, P of x, y is equal to the product of those two marginal PMFs, okay? Which means P of x, y is equal to P sub x of x times P sub y of y. If those two variables are continuous, of course, the joint probability, the joint PDF would be equal to the product of the marginal PDFs if they're independent, okay? And that's one of the way to identify if they are independent or not. So just always keep this idea in your mind. If two random variables are independent, then the joint PDF is going to be equal to the product of the marginal PDFs. If they are continuous, then and they are independent of each other, then the marginal PDF would be equal to, the joint PDF would be equal to the product of the marginal PDFs as shown up here. So once this is clear, let's take a look at the example here. This is a continuation of example 5.1. Let's just take a look at if x and y are independent or not in this case. Let's get back to the 5.1, so which is the very beginning. Here it is. Let me clean this up real quick. Clean it for quick. So okay. So based on the definition we just went over, if they're independent, we're gonna have the joint PMF is gonna be equal to the P sub x of x times the P sub y of y, right? So we can just go ahead and pick up a outer pair. Let's say, what's the probability of 100? So based on the probability distribution here, the probability of 100 is equal to 0.1, right? And then what is the probability that x is equal to 100? The probability x is equal to 100 is, as what we got out here, 0.5, right? And the probability y is equal to 100. The probability y is equal to 100 is 0.25, right? 25. So obviously, this 0.1 is not equal to 0.5 times 0.25, which is the P sub x of x times the marginal PMF of y. So since this is not equal to that, I should have 100 over here instead of x and y. So since this is not equal to the product here, so in this case, x and y are not independent. And that's how we identify if they are independent or not. Now let's get back to the notes. And we'll say that what I mentioned here is exactly the same thing as what we mentioned previously. So P of 100 is equal to 0.1, which is not equal to 0.5 times 2.25, which is the probability of x is equal to 100 and the probability of y is equal to 100. So of course, in this case, x and y are not independent. Okay, for the example 5.7, this is a continuation of the example 5.5. So in that case, we have fxy is equal to let's say 24xy for x is greater than or equal to 0, less than or equal to 1, y is greater than or equal to 2, y less than or equal to 1, and x plus y is less than or equal to 1, right? And we have the marginal PDF of x is 12 times 12x minus 1 minus x squared. Of course, for x is greater than 0, less than or equal to 1. And f sub y is equal to 12y times 1 minus y squared. Y is greater than or equal to 0. That's what we got previously, and you can also check it out from the notes in the last video. So let's take a look what they said over here. Because f of x y has a form of product, x and y would appear to be independent. However, in this case, we have, if we plug 3/4 back into the marginal PDFs, we'll have the value of the marginal PDF would be equal to both of them are equal to 9/16. But if we plug both of them back into the joint PDF, actually this is not appropriate to write a 0 over here, because we're talking about the function value. We're talking about the function value, not the, oh yeah, actually it is 0 because I'm sorry, this is a 0 because in this case x is equal to 3/4, x is 3/4, and y is equal to 3/4. And we have x plus y is equal to 3/4 plus 3/4, which is 6/4, which is greater than 1. And we know that based on the given joint PDF we have, it's going to be 0 otherwise, right? Since x plus y is greater than 1, which is outside of this region, so the function value will be 0. So that means they are not equal, so they are not independent, even though f of xy has the form of product xy. But why? Why this joint PDF has the form of product of x and y, but they're not independent? Because of this. Okay? To be independent, f of xy must have the form of a function of x times a function of y. And the region of positive density must be a rectangle whose sides are parallel to the coordinate axis. Okay, so the reason why x and y are not independent, even though the joint PDF here has a form of those two functions, is because that the region is not a rectangle. So in this case, based on what we got before, we have a rectangle here. This is 1, and this region is the positive density region, which is a rectangle, which is a triangle, not rectangle. Okay, that's why they're not independent. All right. So basically, the key point for here is that if we know two variables are independent, then we're gonna have that the joint PDF or the joint PMF is going to be equal to the product of the marginal PMFs of the product of marginal PDFs. So of course, we can say it backwards. If we have f of x times f of y is equal to f of xy, so they're independent, or p of x times p of y is equal to p of xy, they're independent as well. Actually, we can prove this this case as in a way as what I just said. So since we have f of x is equal to this, f of y is equal to that, obviously the product of those two is not equal to the joint PDF over here, and that's why they're not independent. Okay. All right, independence of two random variables is most useful when the description of the experiment under study suggests that x and y have no effect on each other. So then once the marginal PMFs or PDFs have been specified, the joint PMF or PDF is simply the product of the two marginal functions. It follows that. So if we have they're independent, then the probability x is between a and b and y is between c and d is gonna equal to the probability x is between a and b and the probability y is between c and d. Okay, that's coming from the definition of independence. All right. Once this makes sense, so basically this is going to be equal to, let me rewrite it in a form of integration. Integration from a to b, from c to d, fx y, and then dx dy, right? So since they're independent, then I can rewrite it like from a to b, from c to d, fx times f of y, dx dy, right? Okay. Since if they're independent, we can just rewrite the joint PDF in the form of a product like this. And then we can just kind of rewrite it from a to b, fx dx times from c to d, f of y dy. So based on the property of a double integration, right? Because this is a function of x, this is a function of x, this is a function of y. So we can just separate like this. And of course, this is going to be equal to, the first integration is going to be equal to the probability x is greater than or equal to a to b times the probability that y is greater than or equal to c and less than or equal to d. Okay. This is coming from the definition of PDFs. Now let's take a look at this example here. Actually, I think if you understand the definition of joint PDF or joint PMFs, I think this independence is quite straightforward for you. Suppose that the lifetimes of two components are independent. First of all, they are independent of one another, that the first lifetime x1 has an exponential distribution with parameter lambda 1, so whereas the second x2 has an exponential distribution with parameter lambda 2. Then the joint PDF f of x1, x2. So first of all, before talking about the solution of this kind of problem, let's take a look at a short review on the exponential distributions. For the exponential distributions, we have the PDF f of x is equal to lambda e to the negative lambda times x, right? And x is greater than 0, of course. And then the CDF is going to be equal to 1 minus, I will write it down here a little bit. 1 minus e to the negative lambda x. X is greater than 0, and 0 if x is less than 0. Okay? Okay, that's pretty much the CDF PDF exponential distribution. Now we know we want to find the joint PDF over here. So and which is f of x1 and x2, and we know that those two variables are independent, right? So this is going to be equal to the marginal PDF of x1 and the marginal PDF of x2. So which is equal to, of course, we're going to replace the lambda 1, with the lambda in the original expression. So it's going to be lambda 1 e to the negative lambda 1 times x1 and times lambda 2 times e to the negative lambda 2 x2. And of course, we're going to have both x1 x2 are positive, and then 0 otherwise. Don't forget that. So this is quite straightforward if we know that those two variables are independent. Very easy to find the joint PDF with the given margin of it's very easy to find the margin. It's very easy to find the joint PDF with the given marginal PDFs if those two variables are independent. We just need to multiply them together. Okay. All right. And it says lambda 1 is equal to 1 over 1,000. Lambda 2 is 1 over 1,200. So that the expected lifetimes are 1,000 hours and 1,200 times. 1,200 hours, respectively. So the probability that both component lifetimes are at least 115 hours. So since we are looking for the probability that both component lifetimes are at least 1,500 hours. So in other words, we're looking for that x1 is greater than equal to 1,500 and x2 is equal to x2 is greater than equal to 105,000. Since they're independent, we can just break it into two parts, just rewrite it in a form of multiplication. So which is the probability of x1 is greater than equal to 1,500 times the probability of x2 is greater than equal to 1,500. Now, let's take a look how to find this. How do we get this from here? So actually, I would prefer to rewrite it. So with the probability x1 is greater than equal to times the probability x2 greater than equal to 1. Actually, I didn't do anything new, or I didn't change anything either. I just kind of rewrite it and to make it look more clear. So how we got this? How we calculate this probability? We're going to use the definition of CDF. We know f of 1,500, that would be equal to the probability x is less than 1,500. Actually, we don't have to worry about the boundary points here because it's a continuous random variable. And we're looking for the probability that x1 is greater than equal to 1,500. So we're going to have the probability x is greater than equal to 1,500. It's going to be equal to 1 minus the probability of x is less than 1,500, which is equal to 1 minus f of 1,500. Okay, so what we're going to do is 1 minus, so we plug the 1,500 back into here. It's going to 1 minus e to the negative 1,500. Lambda. Yeah, it's lambda here. So if we simplify that, it's going to be equal to e to the negative 1,500 lambda. So over here, of course, the probability x1 is greater than equal to 1,500 is going to be e to the negative lambda 1 times 1,500 times e to the negative lambda 2 times 1,500. Okay, and that's pretty much how we got this from here. The reason is over here. All right, so and we know the value of lambda 1 and lambda 2. We just plug them back into here. We'll find the final answer. And the key point is that once we know that x1 and x2 are independent, we can just rewrite it in a form of multiplication like this. All right. All right, that's pretty much all about the independence. Let's take a look at the conditional distributions now. This is the background information. Suppose x is the number of major defects in a randomly selected new automobile, and y is equal to the number of minor defects in the same auto. If we learn that the selected car has one major defect, so what now the probability that the car has at most 3 minor defects? That is, what is probability that given x is equal to 1, what is probability y is less than or equal to 3? Similarly, if x and y denote the lifetimes of the front and rear tires on a motorcycle, and it happens that x is equal to 10,100 miles, so what now is the probability that y is at most 15,000 miles? And what is the expected lifetime of the rear tire conditional on the value of x? Questions of this sort can be answered by studying the conditional probability distributions. So before talking about the conditional probability distributions, let's take a look at what is the conditional probabilities we went over before. So if I gave you a probability of A given B, so that would be equal to the probability of A intersection B all over probability of B. Okay? We went over this before. And once we know this idea, actually the conditional probability distribution is kind of similar to the idea we just write it up over here. Let's take a look at the definition here. Let x and y be two continuous random variables with joint PDF f of x, y, and marginal x PDF f of x. And then for any value x for which f of x is greater than 0, the conditional probability density function of y given that x is x. So in other words, we're looking for that the conditional probability distribution of y given x. So we're going to use the vertical line here. So the f sub y vertical line x, that means y given x. Of course, we get the little y given little x here. So based on what we went over here, on the top, we're going to have x and y, or a and b. So which means we need the joint PDF on the top. And then divided by the given marginal PDF on the bottom here. Okay, so if x and y are discrete, replacing the PDFs with PMS in this definition gives the conditional probability mass function of y given x. So basically, if you rewrite it as the p sub y given x is equal to the probability, the joint PMF x to y divided by the marginal PMF of x. Just like that. Okay, so very, very similar to the idea we talked about here. The difference is that over here we talking about two events, and over here we talking about the two continuous two random variables. Okay, and the same thing. There's what is similar between them is that we usually get the probability of a and b on the top, and the probability of the given event or the given variable on the bottom here. Alright, so once this is clear, let's take a look at this example. Reconsider the situation of examples 5.3, 5.4 involving x is equal to the proportion of time that a bank's job facility is busy, and y is equal to analogous proportion for the walk-up window. The conditional PDF of y given that x is equal to 0.8. So in that previous example, I just wrote down the joint PDF and the marginal PDF of x. So the joint PDF is equal to 1.2 times x plus y squared for both x and y between 0 and 1, and 0 otherwise. And the marginal PDF of x is 1.2x times plus 0.4 for x between 0 and 1, or 0 otherwise. Okay? This is you will get those two things from the previous notes as well. So I wouldn't explain why or where I got those two things. So with the given those two things, let's take a look at how to find the conditional PDF of y given x is equal to 0.8. So what do we need to do? Just like a plug and play. So what we know is that based on what we just went over, we know f of y given x is equal to f of x of y, and then divided by the marginal PDF of x, right? What's given here. So what we need to do next is just plug the different numbers, right? So we're looking for the marginal the conditional PDF y given x, and when y given x is 0.8. And then of course that would be equal to, we just replace the x with 0.8, f of 0.8 y divided by f, the marginal PDF when x is equal to 0.8. Okay? And then what do we need to do next? We just need to plug the 0.8 and y back into the joint PDF here. So we just need to replace the x with 0.8. It's going to be 0.2 times 0.8 plus y squared, right? And then divided by, we just plug the 0.8 back into here because 0.8 is between 0 and 1. So it is qualified to be plugged in back into the marginal PDF of x. So which is a 1.2 times 0.8 and then plus 0.4, right? Exactly same thing as what we got over here. Okay. All right. So after the calculation, you just simplified. You will have the conditional PDF of y given x is equal to 0.8 is equal to 1 over 34 times of 24 plus 30 y squared. So when y is between 0 and 1. So I wouldn't go over the whole calculation over here because it's quite straightforward, just like the simplify. All right, so once we got the joint, not joint, what I'm talking about, is the conditional PDF of y given x is 0.8. Let's take a look at how to find the probability over here. So the probability that let me clean this real quick. Oops. So we're looking for the probability that y is less than or equal to 0.5 given x is equal to 0.8. So this is very similar. I mean, I would say this. I would say all the properties of PDF or PMF or CDF or expected values, those properties also applies to the conditional distribution. So when we are looking for, in general, if we're looking for the probability, if we only have one variable probability, we want to find the probability y is less than or equal to 0.5. What we need to do is integration negative infinity to 0.5 and then f of y dy. That's what we usually do, right? So we just integrate the PDF over this interval here. So same thing here. If we want to find this probability given the probability y is less than or equal to 0.5 given x is equal to 0.8, we just need to integrate the conditional PDF over this interval, negative infinity 0.5. Since the y value should be between 0 to 1, so we want to integrate this conditional PDF of y given x is 0.8 over the interval 0 to 0.5 with respect to y. Okay? Of course, I wouldn't go over the calculation over here because it's just like the basic power rules. You just need to know the idea how to find the probability of interval, given x is equal to 0.8 here. Just integrate the conditional PDF over the given interval over here. Okay, and I believe the calculation part is quite simple over here. All right, once this makes sense, let's take a look at the expected values. Using the marginal PDF of y gives the probability y is less than or equal to 0.5 is equal to 0.350. So of course this is just for the probability y is less than or equal to 0.5, but the probability what we found out over here is the probability of y is less than or equal to 0.5 given x is equal to 0.8. Okay, they are different. So this is completely different from this. Okay, they are different. And of course, e of y. So if you want to find the expected value of y, so you just go ahead to apply the definition of expected values. That's going to be equal to integration from 0 to 1. That's the interval of y value. Y times the marginal PDF of y dy. That's how you calculate the expected value of y here. Whereas the expected proportion of the time that the walk-up facility is busy given that x is equal to 0.8. So over here, we're looking for a conditional expectation. So once again, since the properties of the regular PDF or CDF or the expected values or the random variables also applies to the conditional distributions as well. So if we want to find the conditional expectation, we just need integrate y times the conditional PDF over the given interval of y. Okay? So regularly, if we want to find the expected value of y, we do the integration of y times f of y here. So of course, if we want to find the conditional expectation, we want to integrate the y times the conditional PDF here. So that would be, since the interval of y is from 0 to 1, and then y times the conditional PDF. Conditional PDF is 1 over 34 times 24 plus 30 y squares. And that's why we had the 1 over 34. Since the constant number, it could be pulled out of the integration. So we got times 24 plus 30 y squared. And after the calculation, I think what you need to do is just apply the power rule to calculate this integration, and the final answer is 0.574. So the idea, I just put this thing over here just to like let you know that if you want to find the conditional expectation, you just need to do it like in the regular way. So, but the only difference that what multiplied over here is the conditional PDF, but what we usually use for the regular expectation is y times the margin PDF inside. That's the main difference. All right, that's pretty much all about this video.